Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm very happy to have Yair here for his end of internship talk, titled "When is Fair Sharing Optimal?" Yair, all to you.
Thank you. Right, so this is basically what I've been up to during my internship here. And what we've been trying to study was basically ways of dividing profits among self-interested agents in a way that would be nice, would be fair, in a way. So what's the basic idea? So let's take a simple model. We have two people. We have an employee and a factory owner, and they can make money just by working together. And this is a very fundamental economics problem. How should they divide profits in a good way? And there's been a whole lot of literature about this. And basically, a lot of economic models boil down to this. If both people are equally required to generate profits and they cannot make any money on their own, then any payoff division between them is okay. Well, there are, of course, ones that say that they should get equal shares, but in many cases they don't. So kind of giving all the money to the factory or giving all the money to the employee, both are equally fine. And that seemed a bit odd to us, because what actually happens in many cases, when you actually look at how people divide money, is that what they do is they decide upon how they divide their money based on some contract that they agree on ahead of time. They take into account the fact that their interaction would be sequential, they will take place over time, and they sign some agreement to enforce it, and how much money each one of them gets really depends on their bargaining ability. And just to kind of drive the point home of what's the fundamental problem of not looking looking at these games as just a one-shot interaction, let's look at the following setting. So suppose that instead of having just one factory, one worker, we have two workers and one factory. And again, the factory and any one of the workers can just join together and make some money. Let's say they can make $1. And the workers by themselves are worthless, the factory in itself is worthless, but the workers themselves, they cannot work together. They have no value for working together. So a lot of economic models, what they would say in this setting is that, well, the factory here has a lot of bargaining power because each one of the workers on his own can be replaced by the other guy, right? So think about it, that suppose that one worker asks for some money, then the factory will decide to work with him, but then the other guy, the other worker could just say, well, I'll take even less. And that actually happens, right? So when you have a lot of labor in the market and too much labor in the market drives down wages, right? So that's basically the idea of what we're getting here. And what we did want to observe here, what we do want to observe in this model is that this problem arises when you think about the game as just a one-shot interaction. When you start thinking about it as an iterative setting where sequential profit divisions occur, then what we see is that actually the amount of money that you're getting at a certain round affects your ability to produce or to generate profits at the next round, right? So think about, again, this employee. If you don't pay an employee enough, then he won't be able to pay health insurance. He won't be able to buy clothes, buy food, stuff like that. He won't be able to work as well. And same for the factory. Same goes for the factory, right? So a factory that pays its workers too much will not be able to buy machines. It won't be able to, maybe if you give him more money, you'll be able to buy better machines and generate even more profit. So the amount of money you're getting at each round affects the utility that you will get on the next. So far, so good? By the way, if there are any questions, please feel free to stop me. We have like an hour here, so yeah.
So, 2 questions.
Oh, excellent. You see? That was easy. Yes.
Did you invite Andrew Blake to the talk?
We invited everybody.
I mean, he's a message for the management. And the second question is, in some sense, basically, from a very practical setting, if I give my employees more money, right, they will say, okay, now I don't need to be employed. I have enough balance, right? I have enough savings. Now I don't need to work.
Right. So, okay, that's a good question. It's a valid point. We'll talk about kind of what are our underlying assumptions here. So one of the things we're kind of assuming here, we don't really look at what they save for the next round. So you must kind of invest all of your money, right? So that's, but it's a very valid point. Let's talk about this later. Okay. So, yeah. So in this case, what you can think about is the following. We have sequential payoff divisions, and what we want to find situations where such sequential payoff division is optimal. That is, that it maximizes the revenue that people get, the total revenue people get at every round. And then we can ask about these revenue divisions, when are people happy with how much money they're getting? Right, so kind of informally what you have is basically like, they start with some initial bundles, yeah? They take these bundles, they generate a big bundle of money, then they split this money between them. Then, given how much money each one of them has, the next round they generate money. So here, they decided on a somewhat equal share, so they managed to get a lot of money, and then they again split it. But here you see in this round, for example, the factory owner decided to take a lot of the money and the employee got very little. So the next round, maybe they'll just not generate a lot. Okay, so kind of it maybe hit some critical point where the employee just became really useless after getting too little money. And that's what actually happened, and then they got very little. All right? So what we are looking at, okay, so in this setting, what we basically say is that they can, in general, divide the money however they like at every single round. So anything is admissible. But to make things slightly simple, let's look at something we call stationary contracts. Okay, we agree ahead of time on a certain payoff division. Let's say I get 30%, Pushmit gets 70%. Okay, and that's what we're going to do for the rest of eternity. Okay, and then we want to see what happens in this setting. Okay, so slightly more formally. So if it's in the many-player setting, it generalizes, but in the two-player setting, what do we have? We're given a utility function. That utility function is just a function from R2 to R. Okay, it just takes as input how much money each player has and outputs the revenue. Okay, we have initial endowments to each one of the players. Just player 1 starts with some bundle A1, player 2 starts with another bundle A2, and we agree on how we share this money. So it's just a vector such that the sum of the coordinates, it's non-negative, such that the sum of the coordinates is exactly 1. So this is how many percent does player 1 get, how many percent does player 2 get. Okay, and then how does this look like? How does this iterative setting look like? So in the beginning, as I said, each one of them starts with a bundle of A1 and A2 respectively. This is just time. So time 0, time 1, time 2, time 3. Right? And this is how much total revenue they have at every single point. So at time 0, okay, well, they have revenue technically of A1 plus A2, but let's not count this round. And then what happens? Okay, at time 1, they generate revenue of V, A1, A2. Okay, let's call this number V1. And then player 1 gets X1 times that value, and player 2 gets X2 times that value. Make sense? And then on the next round, well, exactly the same thing happens, but now these are the bundles. So again, we evaluate the function on these bundles, on x1, v1, x2, v1. Okay, that's v2. That's how much money they have at round 2. Okay, and again, they share it. So x1, v2, x2, v2. Yeah, makes sense? And then again, so round 3, exactly the same thing happens, and that continues, right? So at round 3, they get this much revenue, and this is how much player 1 gets, this is how much player 2 gets. Okay, and the tension here is between how much social welfare does the contract give to everybody, which is just this number, this v1, v2, v3, vt, and how much utility does each player have. So players, they don't care about this value. They just want to maximize this thing. Okay? They don't care about v3 in itself. If v3 was slightly less, but x1 was slightly more, that would be great for player 1. That's what he wants. Okay? So he wants, that's the tension that we're playing with here. Okay, so on one hand, you have an optimal contract, one that maximizes this thing, and then you have an individually optimal contract, one that maximizes individual utility. and they're not necessarily the same, right? So far, any questions before I move on? This is kind of, you can stop paying attention after this. So does this make sense? Well, don't stop paying attention, but yeah, pay attention. Okay, so let's do a few examples. So let's take as our function, our utility function, to be vxy equals 4 times x times y, right? And let's say that the initial endowments are $50 to each one of the guys, okay? And what happens? Now we're deciding on a contract. So suppose that we decide on a 50-50 split of the profits. So what would be our profits at every single round? So we start with $50 each, as we said, okay? We evaluate the function at half for each one of them. Well, half times 4, that's 1. And then we split that equally, so each person gets $50. And then we just repeat the exercise. So this is going to be their profits till infinity. Yeah? Make sense? Okay, this sounds good, right? I mean, everybody's getting 50-50. It seems to be kind of a stable state, right? Nothing changes, so we're getting the same amount of money every single round, which is not bad. But now let's say that player 1 wants to offer this contract, okay? A contract where player 1 gets 75% of the profits, and player 2 gets only 25% of the profits. Okay, will player 1 be happy with this arrangement? Well, okay, in the beginning, obviously, nothing happens. He still starts with $50. On the second round, well, they generated $1 on the first round, and then they share it 3/4 to him, 1/4 to player 2. And then, okay, you evaluate the function. You can trust me that these computations are correct. But basically what happens, if you notice, you can see some kind of a pattern emerging here, right? So player 1, in the beginning, he is indeed happy with choosing this, right? So in the beginning, he's getting actually more money than what he had gotten under this arrangement. But as time goes by, this turns out to be really, really bad. Yes? So eventually, he becomes quite unhappy with the amount of money he gets. He's getting less than half, and actually the amount of money he'll be getting will go to 0. So it was actually in his own interest to give a 50-50 split. In fact, you can show that anything but a 50-50 split here is bad. Kind of like profits will eventually dwindle down to 0. Yeah? Make sense? Okay. Now, let's take another example. Okay? This is not, okay, so just to ease your concerns, this is not some well-known kind of economic utility function, right? So I don't have any idea of an economic setting where your utility is given by sine something, okay? I mean, if you know of one, please let me know. It will be pretty cool. But this is just for the sake of an example, okay? So you have a utility function that's given by sinus of 2 pi x times 2 pi y, sinus of 2 pi y, and you start with initial endowments of 1/4, 1/4. So this is obviously a constructed example, but the idea is this. So we have 2 optima of this function, okay? You'll have to trust me on that one. You can check it later yourselves. And one of them is when player 1 gets 1/4 of the profits and player 2 gets 3/4 of the profits, in which case what happens? In the beginning, they both get 1/4, and then okay, so this function evaluates to 1 at this point, and it also evaluates to 1 on all of these points, just because it's kind of a cyclic function. And what happens is that player 2 is obviously quite happy with this. He's getting 3/4 all throughout. Yeah? But because this is a symmetric situation, then the same would hold for player 1. So you could also say that 3/4 for player 1 is also a good idea. Okay? It's actually quite nice. So he's getting 3/4 of the profits. Player 2 is getting 1/4, and this is also stable. Okay, so there are 2 kind of equally good or equally optimal ways of dividing profits. These are optimal points of this function over the domain. And there are 2 equally good ways of dividing profits, and one benefits player 1, one benefits player 2. Make sense? Okay. So now let's look at what happens. So we want to find the relation between how much money do you get as an individual, or what is your individually optimal contract, and what is socially optimal, okay? And we can actually find it. So we can actually derive these functions mathematically using calculus, basically. So let's take the first function we had. So it's a v of xy equals 4xy. So both players, again, start with $50. And let us just write vt of x to be the social welfare at time t if player 1 gets a share of x and player 2 gets a share of 1 minus x. So x% and 1 minus x%. Yeah? And let's call ut of x to be the utility of player 1 at time t. Okay? And player 1 wants to just maximize this function at every round. He's greedy. He wants at time t, I want to know what is the best thing for me to do at time t. Okay? And so let's graph it. Let's graph it for t from 2 to 9. So what happens here? Dave commented on the colors before, but yeah, I didn't change them, but let me just explain. So this is t equals 2, t equals 3, t equals 4, and so on. This is just the value of x, and this is the utility that player 1 is getting. Okay? And we want to find a value of x that maximizes these utilities. So this is his utility function as a function of the share he's getting at time 2, at time 3, and so on. And what are the maxima of these functions? Well, if you notice, they seem to converge. Right? They converge. And they do converge. They indeed converge. You can verify that if you want. And they converge to this point here, to the 50-50 split that we saw before. That's neat, right? I mean, basically what happens is that as time goes by, yeah, you do want to get a little more for yourself, but that more that you're getting for yourself seems to be actually aligning with global optima as time goes by. Okay? So it's not at the global optimum, but it converges to it. And you can actually prove this. So take this function and do this exercise, you can actually show it. Yeah? Am I making sense? All right. Now let's take another function. Now this function is v of x of y is x to the power of 1/4 times y to the power of 1/4, and both players start with an endowment of $1. All right? And again, the same setting, vt is just the social welfare at time t, and ut is the utility of player 1 at time t, which is just x times the total welfare at time t. All right? And he wants to maximize this function, and again, we graph these for times t equals 2 to 9. All right? And now, okay, so this is his utility function as a function of x at time 2, at time 3, at time 4, and so on, and the little guy here at the bottom is at time 9. All right? So this also converges. But this time, it doesn't converge to the globally optimal strategy, to the globally optimal contract. Okay? The best thing for the players to do in this setting is to do a 50-50 split of the money. That will give them kind of maximized profits as time goes by. But this is not what happens. This is not what happens from the perspective of the player. From the perspective of the player, you do get convergence, but it won't converge to something that is globally optimal. His incentives do not align with the group's incentives in this case. Okay? So you do get convergence, but not to the optimal contract. Okay, so sometimes you do, sometimes you don't. Finally, just one last guy. Let's say that the value of xy is, wait, are there questions about this? Does this make sense? Okay, so there's this setting and there's this setting, kind of like two very different things. Okay, and let's take one final example. Let's say that the value of xy is just, 2 isn't for normalization, minimum of xy. Okay, so look at how much money each person has, take the minimum of that, and then multiply it by 2. All right? And they both start with $1. And again, the utility of the player at time t is just how much utility the group has, time his share, the share that he gets, and he wants to maximize this at every single time point. So what would it look like? Again, if you notice, this is the graph for time 2, 3, 4, 5, 6, and so on, and the deep blue one in the inside, that's at time 9, right? And where is the maximum of all of these functions? The maximum of all of these functions is at the 50-50 split, right? And that 50-50 split is, in fact, the optimum of this function, right? So in this case, it's not that player one wanted a little bit more at every single round, and that turned out to converge to the optimal strategy. But indeed, in this case, he actually wants to do what's good for the group. Okay? The best for him is actually what's good for the group. So we had one case where you didn't want to do what's good for the group, but it kind of moved towards there as time went by. One case where you didn't want to do what's good for the group at any point of time. And one case, in this case, where what you wanted to do was exactly within the incentives of the group. Right? Am I making sense? Okay. So the basic question that we want to ask is, when is it that what people perceive as fair, what people want for themselves, the individually optimal shares, when do they get to become optimal? Okay? So the first question is, does it even happen? Okay? Does it ever happen? And the answer is that if v is a differentiable function, then no. Okay? So actually, what we saw here could only happen because this function is not differentiable. Okay? At least not at the point of maximum. Yeah? It's not differentiable at the point 1/2, 1/2. Okay, it looks like a hat, right? So in this case, just because it wasn't differentiable, you had this event that individually optimal actually became optimal. But if it was differentiable, as we've seen before, you may get this convergence, or you may not, but you will never get actually that optimal is what you want to do. You would always want a little bit more than what you're getting. Okay, there's this inevitable tension between what's good for the group and what the individual wants in our setting. Which I thought was a tragic result, right? I mean, it kind of says something sad about human beings, right? So even if you know that what we are doing now, the sharing that we're agreeing to now, is what's actually best for everyone, you don't want that. You don't want that. You want what's best for yourself, and there is no way to persuade you otherwise if the function is differentiable. So it's a bit interesting, right? So you're assuming that your players know they know how to trade and they know calculus. Yeah. So yes.
If you add some noise, so you decide an allocation, right? So I'll basically say this is what I want. And after I have told my bid, now you will give me my share, and then you say, no, I'll not give you your share, but I'll inject some noise.
Okay, so a quick answer is I don't know, because I mean we haven't really looked at that, but my guess is that if that noise is small enough, then what I'm about to say would still hold. Okay, so I'm going to kind of say something about the convergence, and then like between individually optimal to the optimal, and I believe that it would still hold even if you have some noise there. But noise, actually, we discussed this somewhat in what's related to this work, and you do get this model of noise in portfolio selection, right? So you have a model of stocks. You want to know which stock to invest in, but they have some noise on how much money you will get from them. And then and that affects your choices for future rounds. So in that sense, maybe that's what you're trying to get at. Yeah. So it is certainly a very similar model, but yeah, I mean there is some difference here also in the setting. So here, if you want, the stocks actually want to maximize their own profits, right? So but yeah, I mean that is a direction we have thought about. We haven't studied it during this time. Yeah, but it is very relevant. So. Yeah, as I said, indeed, if the function is differentiable, there is going to be an inevitable tension between what's good for the group and what's good for the individual. The individual will always want a little more. Could it be a lot more? So let's look at when is it that an individual will want more, but not a lot more. So just as a reminder, for those of us who haven't looked at these things for a while, we say that a function from Rn to R is homogeneous if for any vector x and any constant c, the value of c times x is just c to the power of k times the value of x. All right? And basically think about it like this. suppose that you have homogeneity of degree 1. So what does that mean? That means that, let's say, Pushmit and I come into the table, and both of us have X money and Y money, and then I get 100 times X, and Pushmit gets 100 times Y. Then what our value would be is just 100 times the value that we had gotten before. Okay, so 100 times more resources translates to 100 times more profits. If K is more than 1, that means we're getting more than 100 times. We're getting kind of 100 to the power of K. And if it's less than 1, then we're getting less than 100. So we have decreasing returns on our money. Yeah? And well, one thing that we kind of observed as we looked at this problem is that homogeneous functions are nice. They're really nice and easy to work with in this setting because basically what we want to do with the basic question is to find this optimal stationary contract. And that's in general not very nice to do if your function is just anything, because you need to do this recursive thing, right? You need to evaluate the function, share it, and then reevaluate at that point. So if the function is homogeneous, then this becomes much easier. You can actually find it, you can find a closed form formula for this VT, and you can actually rederive an optimal contract quite easily. So that was already nice. But more than that, what we found, this is kind of the main result of what we did. So if you weren't paying attention from the time I told you you can stop until now, pay attention again. So if V is a differentiable function and it's homogeneous of degree K, okay? So if K is greater or equal to 1, then individually optimal contracts converge to a critical point of V. Okay? So it's a point where the gradient of V over the kind of constraint to the stationary contract space is 0, right? And basically, so this means that individually optimal contracts converge to critical points. Otherwise, they do not converge to critical points. All right? So what does that mean? That means that, in particular, if V is a strictly concave function, well, if it's strictly concave, that means that the only critical point over the space of contracts is a global maximum, right? So what does that mean? That means that if you have a differentiable, homogeneous, and strictly concave function, then all individually optimal contracts eventually converge to a globally optimal solution. So as time goes by, individual incentives and group incentives become 1. You do not want to change you do not want to deviate from the group optimal solution, at least not by much. So again, as I said, you will want to change it, but the change becomes infinitely small as time goes by. Does this make sense? I thought this was actually quite nice. So I really like this idea. And I actually like this bit a bit more. Because what does this say? This actually tells you of a situation where you're guaranteed to not have convergence. You're kind of told, when will you never have an alignment between individual incentives and group incentives? So in this setting, so basically if V is a differentiable homogeneous function of degree K, where K is strictly less than 1, then never, under any circumstances, will players want to do what's good for the group. Make sense? Okay. So now let's, any questions? Okay, good.
Is it that it doesn't converge, or does it converge but not to?
Okay. So what I'm not saying here, so I need to be slightly more precise. So if you have a sequence of ones that converge, if you have a sequence of such contracts that does converge to something, then it will converge to a critical point here. And here, basically what it says is that no convergent sequence of such individually optimal contracts will converge to an optimum, okay? If it doesn't converge, then it doesn't converge, right? Then kind of, I mean, then you can't say anything really.
So I'm trying to understand whether the agent doesn't have any optimal thing that he can do, or whether what is optimal for the agent differs from what's optimal for the group.
Okay, so when I say optimal for the agent, I'm talking about optimal at time t. Right? So it will be kind of a sequence. So at every single point, you need to choose something that's best for you. So a priori, kind of there's no reason to assume that this sequence will converge to anything. Could be, but all I'm saying is that if it does, then under the above conditions, then it will converge here, and it will converge to an optimum, to a critical point here, and it will not converge to a critical point here. Yeah? And this, notice, this is just saying a critical point. Okay? So it could actually, so it could be a local maximum. It's not even guaranteed to be the global maximum. So we actually have examples where you get convergence to a local maximum, something that's kind of good for the group, but not the best. Okay? So that's also possible. But of course, this doesn't happen if the function is just kind of a hill, right? If it's strictly concave, then this doesn't happen. So let's look at a few functions that are strictly concave and do occur in kind of rather commonly in economic literature. So the most general case that we could find was CES production functions. So CES production functions are generally, so they do appear quite often in economic literature. They have these nice properties. They have some uniqueness properties. So they're the only functions that satisfy some nice economic properties. And basically what they do is they do some sort of a weighted average. Okay, so given a vector x, what they do is they take xi over ai. Ai is just some positive constant. And then they take the power of that to the power of r. They average that, and then they take all of that, and they take the rth root of this. Yeah? Well, 1 over r. So what happens here? Well, notice that if these functions are one homogeneous, okay? So that's actually easy to verify, right? And we know that if r is strictly less than 1, so if r equals 1, this is a linear function, okay? If r is more than 1, then it's convex, and if r is less than 1, then it's concave. Concave. So it's concave. It's strictly concave if r is strictly less than 1. And then, indeed, our results will hold. And what it says that if you have a CES production function such that r is less than 1, then any sequence of individually optimal contracts will converge to an optimal solution as time goes to infinity. Yeah? So that's nice. I mean, this is a nice class of functions. Make sense? Another class is Cobb-Douglas production functions. So here, this is, if you notice, a generalization of the 4 times x times y that we have seen before, right? We have seen that, that example just now. And here we have again, so if you are given a vector in Rnx, then it's just c, some constant, some positive constant, times the product of xi to the power of ai. Okay, and this is just some nice result. It's just that the limit as r goes to 0 of the CES production functions, is written here, is just the Cobb-Douglas production function. All right? And that, by the way, is why we have this 1 over n here. So that's why we don't kind of tuck it into the constants, just so that we can, I mean, just because then it converges to exactly this. It's just nice. And what you notice here is that this function, if you look the sum of the AIs, I didn't write this down. Okay, so this function, if you look at the sum of these AIs, then it's homogeneous of the degree of the sum of the AIs, right? So kind of, you can think about it for a second. Then if you kind of multiply each one of these xi's by some lambda, right? Then what you will get, you can extract out lambda to the power of sum of these AIs, right? So it's homogeneous of the degree of the sum of the AIs. So if the sum of these AIs is strictly more than 1, so weakly more than 1, then our results again hold. And then any individually optimal contract will converge to a sequence of individually optimal contracts will converge to an optimal contract. But if the sum of these guys is strictly less than 1, then it won't converge. In fact, we can show what it does converge to. Okay, that's just by analyzing, just doing analytics on the function itself. And so what we get here, and in fact, notice that this is a, so we've seen the case of x to the power of 1/4 times y to the power of 1/4. So that's just a special case here. And if you recall, in that case, indeed, we didn't get convergence to the optimal contract. Yeah, remember? Okay, cool. And again, the min function that we have also seen before So this is called Leontief production functions, and they're just the limit as r goes to minus infinity of these CES production functions. And it's just C times the minimum of xi over ai. Okay, so now what do we know about these functions? Well, we know that these functions, well, they're concave, right? They are homogeneous of degree 1. That's also fairly easy to see. Multiply everything here by some constant lambda, then you can just take this lambda out here. Yeah? So they're homogeneous of degree 1, they're concave. But we're missing something to apply our results, which is differentiability. Right? These functions are not differentiable. So we cannot just apply our results. It doesn't apply. We really kind of rely on differentiability in the theorem. We use Lagrangians and stuff like that. We do need the function to be differentiable. So our results don't immediately hold. So what can you do? Well, we can look at the Leontief function and just manually prove that the result holds. Okay, I mean, you just do the math. It's not a very difficult function to analyze. It's just the minimum of some numbers. It's not so bad to do that. But we can actually do something slightly nicer, and that something slightly nicer will be later useful. And this is we claim the following holds. If you have a function, a utility function v, and that function is a limit of a sequence of differentiable homogeneous functions of degree k or greater to equal to 1, then the same results hold. Okay? So if you have a function that is not in itself a differentiable function, but you know that there is a sequence of differentiable functions that uniformly converges to it, then we can still apply the same theorem. Making sense? And as I said just now, the Leontief function is the limit. These functions, the CS production functions, converge uniformly to the minimum, to the Leontief function. So our results do hold. Okay? So that was a nice bit. Okay? Now wait, any questions so far? Do I make sense? Cool. Right. So now let's try to continue getting some mileage out of that result of the sequence of if the function is not differentiable in itself, but it's the limit of a sequence of differentiable functions. Let's try to get some mileage out of that. So let's look at network flow games. So I hope all of you are familiar with what network flows are, but what's a network flow game? So a network flow game basically is a network flow. So we have a directed graph, we have a source and target vertex, and each edge is a player, right? And the value of the network is its maximum flow. So who are the players here? The players here are just the edges. So each edge is a player, all right? And each edge's resource is just the capacity that it has, all right? And what we do is we say that kind of given the amount of money that you have, you just multiply that amount of money by the initial edge capacity, and that's your new capacity, okay? So you want to find this maximum flow, and then what you want to do is you want to divide the profits of that flow between the players. Okay, so there has been some literature on that. I'll get to that in a bit, but let's first see how our results apply here. Wait, so the setting makes sense? All right, so again, given the amount of money each player has, what we're doing, we're just multiplying that by the initial edge capacity, and that's the new capacity. Think about it that what we have is that we get these initial edge capacities, and the initial endowments vector is just $1 each. Okay, that's another way to think about it. And what we have is a value function that is homogeneous of degree 1. Well, if you multiply all the edge capacities by 100, you'll get 100 times more flow through that network. Okay, exactly 100 times more. But it's not a differentiable function. Right? So, but it is the limit of, it's the uniform limit of differentiable functions. Okay, I'm not going to kind of give a full-blown proof here, but here's an idea. So what do we know? We know by the max flow min cut theorem that the value of the flow, given these endowments of money, is just the min cut. Okay, and how does that look? Well, let C be the set of cuts. Just choose the minimum cut and look at its capacity. Okay. So think about these CTs as just matrices that represent the cuts, okay? And Well, as we know, the min function is just the limit of the CES production functions. But notice this is a bit different from before. Here we're not taking the average over the players. We're taking the average over the cuts. Yeah? So here, it's not 1 over n, the number of players or the number of edges. It's 1 over the size of C, the number of cuts in the graph. Okay? So we're normalizing over that, and we know that these functions are differentiable. They're concave, and when r is less than 1, and we know that they're differentiable. Okay? So we know our results hold, and we know that this thing is the limit of that. So our results hold for network flow games. Okay? Make sense? So what does that mean? Well, that means in particular that if the game has a unique maximum flow, then all individually optimal contracts converge to the global optimum. Okay? Basically, if there's a unique optimum, then we know that we're good. Okay? It may not be, so we have counterexamples, right? So you can easily construct networks where this doesn't hold, in which case you will have players that are unhappy with the global optimum. Basically, some guy who has a less useful edge, but you can still pass flow through it, he would want the flow to pass through him because then he will get some money. But that would not be good for the group. Okay? So if that kind of thing doesn't happen, then our results hold. All right? And another thing that's incidental is that we can actually find a global optimum in polynomial time via linear programming. So what do we do? Well, I'm not going to go into the details of this linear program, but basically what we did is that this is the linear program to find the maximum flow in the original graph, but what we do, we add these kind of share parameters here. So just the flow must be at most the capacity times the share of the money that you get, okay? And we need that the shares sum to 1, as we said. Okay, so that's just the way to find them. I just want to stress, as was not clear in a previous iteration of this talk, what we're doing here, the optimal solution here, will clearly not find a max flow of the original graph, okay? Because the capacities of the edges are much, much less. Okay, these XEs are kind of like you're normalizing the edges capacities by a lot, actually. So they won't have the same flow. They actually have, this actually is pretty cool, and we haven't studied it fully, but there is something really nice there. If you're interested, we can talk about it later. But basically, the idea is this. So what we can show is, okay, so suppose that we get an optimal solution for this linear program that I just showed, okay, which we found in using some LP solver, okay? And we get these XE stars, that is the share of every edge, and FE star, which is the amount of flow that passes through that edge in this linear program. Then, just by kind of switching around sides, we have that XE star is at least FE star over CE star. And what we can also show is that if in the original graph you did pass some flow, then this thing will also can be positive, okay? So basically what that says is if you pass some flow in the original graph, then you will get some share of the profits, okay? And in a sense, the more flow you pass, the more money you get. But the more wasteful you are, so kind of the larger your capacity, the less share of the profits that you'll get. Okay, so there's kind of a proportionality to our payoff division. Make sense? Okay, of course, I'm kind of a bit lying here because this doesn't need to be tight, but this is generally what we're getting. Okay? And what does this mean? Okay, so how does this fare against other payoff divisions? Okay, so you can think about this as follows. So XE star is just a percentage of the money that you get for passing the maximum flow. Okay, this is how much money you're getting. Okay, so forget for a second the iterative setting. Okay, suppose that we're just looking at the graph. We have this max flow problem. We're passing a max flow through the graph. We need to divide the values of these max flows between the players. All right? We don't care now about the iterative setting. Okay, just a one-shot game. And we can actually use this as a payoff division method, right? I mean, this is just saying what percentage of the profits each one of the players gets, right? We can just use that, that's fine. Okay, stay strong, we're almost done. So, so what we get here is the following. So let's compare that to another well-known solution concept, which is the core. So how many people here know what a cooperative game here is? Well, yeah, okay, good. Distinct kind of no from the programming languages people in the so okay. So basically, what's a cooperative game? I'm not going to go into it too much in detail in the general context, but here, what does it say? Well, think of, again, the edges here are players, okay? They want to maximize their own profits. And you need to come up with a way of dividing the value of the maximum flow in such a way that is fair or nice in some way, okay? And one very well-known way of doing it is called the core. And what does the core say? It's basically the set of all payoff divisions such that the total amount of money that each subset of the edges gets is at least the amount of flow it can pass without using any other edge, okay? So think about it like that. These edges need to be, this set of edges says to itself, well, if we're getting less than what we can just pass on our own, then we're not agreeing to this, okay? And that needs to hold for every subset. And in fact, there is a very simple way of ensuring stability in a network flow game, and that's just by paying the min cut of the graph, okay? So in this case, what we do is we just pay 10 here, and we pay 4 here. Okay, so we pay just pay the min cut of the graph, the amount of flow that they pass, and pay nothing to everybody else. All right, and that's stable, right? I mean, no subset of edges can complain, right? I mean, okay, these guys are not getting any money, right? So these two edges here at the bottom, they're not getting any money, that's for sure. But what can they do about it? What can they do about it? I mean, we're not happy with the payoff that we're getting. Fine, what can you do? How can you object? You can't pass flow by yourself. You need them, right? But that's, let's say, on a normative level, that doesn't sound very fair now, does it? It's not like those two edges here live in a vacuum, right? I mean, there is some notion of mutuality. They're certainly not the only min cut on this graph, right? Other people should be getting paid as well, but they're not. But in our payoff setting, they would have been, right? They would have been getting paid. If you passed any flow, you would have gotten money. You would have gotten some share. The more flow you would have passed, the better you would have been, which is great. That's, in my view, that's better than this. So does this make sense? Okay, I hope that I kind of made the connection between fairness and stability apparent. And basically so what kind of take-home messages do you need to take from this talk? Okay, first of all, profit sharing is awesome. Study it. Second of all, I think that one thing that has been kind of overlooked in theory a lot is long-term profits, okay? So there are works on that, there is a lot of work on that, but not in the kind of, in the terms that we're looking at it here, kind of in ensuring fairness or long-term fairness in this way. And I think that there is still a lot more to be done in this setting. But of course there are downsides here. So one is that optimal contracts are of course never individually optimal, assuming differentiability, which I think adds actually kind of a nice tension here, right? So kind of saying something like, me as an individual, I will never be happy with just doing what's socially optimal. I want to drive to do better for myself. And again, as I said, our results do show something positive, that even though there is this tension can be very, very mitigated as time goes by. In fact, I didn't say it before, but as the degree of homogeneity increases, then the convergence becomes faster. So if you have really high returns on investment, then you really have kind of like really fast convergence of individual gains to optimal strategies. Yeah, and yeah, just to conclude what we looked at, so we had like this nice natural profit sharing dynamic, and we show just when individuals want to do what's good for the group. And as I try to kind of touch on applications, so apart from those well-known economics functions, so I think that there is a lot more to go. So network flows, we kind of just touch on them. We didn't really go into too much depth. I think that there is a lot more to go there. There's also settings where weighted matchings, exchange markets that we looked at, and basically any setting that you can think of, that you have a bunch of agents, they would want to cooperate, there is some kind of positive there is some positive value for them working together, and they have some notion of resource, let's say money or time, then I think this can be applied. And just a word on what I would like to see here. So of course, work on kind of any of these application domains would be nice. And looking at other contracts. So what we've looked at is a flat rate contract, right? Just doing one thing, one kind of sharing scheme all over time. So there could be others. So I mean, there are others, and we have done some kind of preliminary work on that, and it shows that by doing something dynamic, you can actually do much, much better than stationary contracts, which is hardly surprising. Okay, so you can do better both as an individual and as a group. Okay, by changing dynamically how much money is allocated at every round. Okay, so that's another nice thing that might be useful. And I talked to people, and it seems that this can be applied to not just resource allocation. So there is, I'm not sure how much this could work, but to just general preference settings. So anywhere where there's like individual preferences and they need to kind of aggregate them, so think voting or something like that, and aggregating them, but the way that you aggregate those preferences would affect what decision will be made or your own preferences in the future. So that might actually be another nice direction, kind of taking it beyond just divisible resources. And yeah, and that's it. Thank you for coming, and that's it. Any questions?
Thank you, first.
Any questions? Yes. Oh no.
Do you think your results will survive if you throw in discount factors?
So we talked about discount factors. Okay, so the short answer is I'm not sure. I think that we need to study it. I think that they will. I think that they will. Anything else? Yes?
So in the network flow game, basically this situation that certain edges are not used in the max flow, that's quite restrictive, right? Because it happens quite often, even in the example that you showed.
Right, right. So the idea is, okay, so of course these are just, so this is obviously a very limited setting. So we assume something that's called mutual dependency. Basically, the idea is that everybody in the group is needed in order to generate profits, okay? Our results don't totally break down if you don't assume that, but what basically happens is that you need to have like this initial stage where you weed out whoever you can, and then start iterating. You kind of negotiate, you see, well, okay, we can do without this edge, you're not getting any money, you can go home, and then just continue from there. Of course, that, if you talk about, for example, uncertainty, then that might be dangerous, right? So you do want to keep redundancy in your graph, and you do want to maybe maintain that thing. So again, that goes beyond stationary contracts, right? So if you want to do that, then you'd need to somehow kind of ensure payoffs are reached to every person. Because remember, if a person is not getting paid at a round, okay, at the next round, he doesn't get any money, he doesn't get any resources. He's as good as useless. So either you assume something like what you mentioned before, that you're allowed to save some money on the side, or you are allowed to kind of forgive for one round and still be useful on the next. Yeah. So that's of course a very valid expansion of the model. Yeah. Any other questions? Okay.
About non-stationary contracts, so how much loss there is in limiting yourself to stationary contracts?
Oh, there could be quite a lot. So there could be kind of exponentially more money derived if you do. So
natural utility functions.
Yeah, exchange markets. So think about exchange markets, okay? So it's a setting where you have a graph, and each edge on the graph has a utility, a pairwise utility function for the agents collaborating. Think about an authors collaboration network, or just a barter market or something like that. And what basically we can show is that stationary contracts can be not bad, okay? You basically, I mean, it's not bad, but if you want, what you could actually do, and I mean, I believe it can be done in polynomial time. There are people who disagree, but I believe that what you could do is basically kind of, as time goes by, you look at who is the most useful exchanges, who are the most useful exchanges on the graph, and as time goes by, kind of just push all the money to them. Okay, just slow, like at every iteration, just give money to the people closest to them. Eventually, all the money will go to the most useful edges, and then just let them run. Okay, and then just let them run. So you cannot do this on a stationary contract, of course, but if you have dynamics, you can you can do that, and then that's actually better. So for really simple networks, like take whatever, like a 3-player with 2 edges between them, then that obviously works. Like that actually obviously is better.
And that contract would still be stationary dynamic.
Maybe, in some sense, yes. It will eventually it will become a stationary contract. Yes. So maybe there is some nice conjecture here, right? So kind of like that any optimal contract kind of stabilizes. You know, that doesn't sound kind of unlikely, but yeah, I mean, then you can ask, what is it stabilized to? And then that actually could be a really cool question. Yeah. Anything else? On a note, I mean, I don't know, so maybe that's relevant to only some people here. I don't know what the relation is between the fair sharing scheme and Shapley value in networks. So that might be relevant. I mean, I don't know. So there is another notion in cooperative games that's called the Shapley value, for those of you who are not familiar, that basically tries to capture some notion of fairness. Okay, so usually in classic cooperative games, when you ask what's a fair payoff division, people would say Shapley value. Okay, but so this is not the Shapley value, and not that I can tell, at least. And I don't know what's the relation. Okay, so for one thing, this payoff division is not symmetric, which the Shapley value is. So there are some things to explore, though. Yeah. Cool. Anything else? Thank you.